Alright, so in today's lesson we're going to talk about acceleration. So we've gone over things like distance and displacement and position, and then we did speed and velocity. Today we're going to talk about acceleration. Okay, now acceleration is a vector. Acceleration is a vector, and it represents the rate of change of velocity. So because velocity changes, we write delta v, and that's also a vector. Okay? And then it's the rate, so we divide by a time interval. So for example, if you're at a red light and it turns green, then you accelerate from 0 to 60. That's going to happen over a certain time interval. Okay? And then you can calculate the acceleration. Now, previously we've had like a scalar component, right? We've had displacement, which is a vector, and then distance, which is a scalar. We have velocity, which is a vector, and speed, which is a scalar. We don't really have a scalar definition for acceleration. Acceleration is a vector. But what makes things confusing is the word deceleration. Okay, deceleration is a word we commonly use in English, but it is not a word that we use in physics. And let me explain why. The reason is, in English, when we use the word deceleration, we usually mean it when something is slowing down. But in physics, because acceleration is a direction, it's a vector, and so it has a directional property, we simply say positive acceleration or negative acceleration. Now, a negative acceleration is still not quite the same as deceleration. So let's use this as an example. So I have a ball and I throw it up, it comes back down. Okay, now as it goes up, right, it's slowing down because gravity is accelerating it downwards. Right? Everywhere on the earth, gravity accelerates stuff down. So as it goes up, it's slowing down. Then it reaches its peak, and then it starts coming down. And as it's coming down, it's speeding up. All right, so usually we like to say up is our positive direction. That means gravity is a negative acceleration because gravity acts down. Okay, so as the ball is going up, it's slowing down due to a negative acceleration. But I say it's not the same as deceleration because then as the ball is coming down, it's speeding up, but it's still due to a negative acceleration. Okay, so deceleration is not a term we're going to use. We're going to use acceleration and negative acceleration. And if you want to try to figure out whether or not something is speeding up or slowing down, you need to look at its velocity. So let's look at this example again. As the ball is moving up, so its velocity is up, but acceleration is down. So the direction of velocity is opposite to the direction of acceleration. Right? When that happens, the object slows down. So when your direction for velocity is opposite to acceleration, you're slowing down. Now on your way down, velocity is actually down, and so is acceleration. So in this case, when your velocity and acceleration are in the same direction, you speed up. So that's just a good thing to remember, right? If velocity and acceleration are the same direction, whether it's both up, both down, or both right, or both left, you're going to speed up. If they're in opposite directions, whatever that is, that was hard, right, then you're going to slow down. Okay, but we're not going to use the term deceleration in physics. We're also going to talk about average acceleration. So if you're going, say, again, let's say you go from 0 to 60, it's going to happen over a time interval. Now your acceleration, your instantaneous acceleration at any point in time might be slightly different from other points in time during that time interval. So we like to talk about average a lot in this course. So over that course of 0 to 60, which I don't know, maybe took 3 seconds, right? We're going to talk about average acceleration. Now, the units for acceleration Let me go back to the equation here. So units for velocity, well, kilometers per hour, but the base units that we use are meters per second. And the base unit of time that we use is second. So we're going to have meters per second, or we say meters per second squared. And so the units are meters per second squared. So what does that mean? It's easier to think of it as meters per second. So distance is good, meters. Velocity, meters per second. So how many meters you travel for every second. Acceleration, meters per second, meaning how much your velocity changes every second. So let's look at an example. Let's say your acceleration is 1 meter per second squared. So if you start off with a velocity of 0, after 1 second, you'll be going 1 meters per second. After another second, 2 meters per second. After another second, 3 meters per second. So it means every second, your velocity increases by 1 meter per second. That's what we mean by 1 meter per second squared. Now there's lots of devices to measure acceleration, just like there is devices to measure distance, like a ruler, right? Or you can have like lasers measure the distance between something. By you can have like echolocations, like radar. You can also have, for velocity, you have radar guns, right? For acceleration, we have something called accelerometers. And the basic idea is this. So let's say you have like a tube with some balls in it. Now initially, the balls under gravity will just sit at the bottom. In this case, they're called, so the beads. The beads will just sit at the bottom. Now if you accelerate in one direction, you can imagine something hanging from your rear view mirror. If you accelerate forward, okay, they move back because they want to sort of stay where they were. And we'll talk about more about that, why that happens when we get to forces. But they want to sort of stay where they were. So based on how much they move back by, you can actually calculate the acceleration of whatever it is you're trying to calculate. So let me pause there. All right, so we're going to try some problems then. So here's our equation. So we have average acceleration is change in velocity over time. And remember, change is always final minus initial. Just like when we did displacement as being the change in position, we would write our final position minus our initial position. Whenever you have that delta symbol, it's final minus initial. Now technically time would be final and minus initial as well, but usually when we get a time interval, we say it took 7 seconds. Right? We don't usually say we started at 0 and ended at 7. And you could, and therefore you do 7 minus 0, which is 7. But usually when we measure a time interval, we just say a certain event took 7 seconds. So that's telling us what delta t is right there. We don't have to calculate it at all by using final minus initial. Okay, so there's our equation. You can put it in a triangle like this, where you'd have delta v at the top, acceleration and time, and you can rearrange. Just remember, this will still need to be expanded into Vf minus Vi. So let's start with the first question. Here we have a motorbike starting from rest. Now, a lot of times I will say that. I will say something starts from rest. What that means is the initial velocity is 0. I'm not going to write this every time in every question. I'm not going to say brackets Vi equals 0. If I say something starts from rest, that means, well, it starts with a velocity of 0. And undergoing uniform acceleration. Uniform means constant acceleration or unchanging acceleration. In this class, we're not going to talk about a changing acceleration. Reaches a velocity, okay, again, right, when I say like reaches a velocity or comes to a velocity or finishes at a velocity, it's talking about final velocity. I'm not going to always write that. Of 21.0 meters per second north. Of course, we still have directional properties because these are all vectors. In 8.4 seconds. Find its average acceleration. Okay, so let's write our given. we know that the initial velocity is 0 meters per second. We know that our final velocity is 21.0 meters per second north. And they give us the time interval, 8.4 seconds. Okay, so in this case, we can use the equation above. We actually don't need to rearrange anything. So average acceleration is v final minus v initial over time. Our final velocity is 21.0 meters per second north minus initial velocity, which is 0. Divide by the time interval of 8.4 seconds. Plug it into our calculator, and we get 2.5 meters per second squared. And again, this is a vector, so we have a directional property. It's going to be north. Okay, it'll be whatever direction you make this. If you want, you could write it as south, but then you'd have to change it to negative 2.5 meters per second. And then we just write our therefore statement. Its acceleration is 2.5 meters per second squared north. Okay, we'll just quickly pause. All right, question number 2. Here we have a cyclist traveling initially at 14 meters per second south. So our initial velocity, 14 meters per second south. Brakes smoothly and stops. Okay, again, I'm not going to write this all the time, but if I say something comes to a stop, that means its final velocity will be 0 in 4 seconds. So there's our time interval. What is the cyclist's average acceleration? Okay, so we're going to use the same equation. V final, always final minus initial, over our time interval. In this case, our final is 0, and then we're going to do minus 14 meters per second south over 4 seconds. Now, in this case, when we calculate this one, we get a negative number. We get negative 3.5 meters per second squared south. That negative is telling us a directional property. So instead of writing negative south, we can write positive north. So 3.5 meters per second squared north. And that makes sense because, like I said before, if you're slowing down, your acceleration velocities are in opposite directions. So in this case, we're slowing down. We're going from 15 meters per second to 0. So our velocity is south, but our acceleration is north. Okay, I'll pause. All right, question 3. When a hockey player hits a hockey puck with his stick, the velocity of the puck changes from 8 meters per second north to 10 meters per second south. So the direction changed. The puck was coming this way, and then it was hit, and now it's going this way. And all that happened over a time interval of 0.05 seconds, so it was very quick. What's the average acceleration of the puck? All right, so let's write what we know. Initial velocity was 8 meters per second north. Final velocity was 10 meters per second south. And our time interval is 0.050 seconds. So to find acceleration, again, final minus initial over time. In this case, we have 10 meters per second south, and then we're subtracting 8 meters per second north. We can't do that just yet. We have south minus north. So what we're going to need to do is change north into negative south so that they're both south and we can properly add the vectors. So we're going to have 10 meters per second south and subtract, and let's put this in brackets now, 8 is going to change to 8 north is going to change to negative 8 south. Now when we do that, we're going to have a double negative here. And that double negative is going to give us a positive, so we're going to end up with 18. So 10 plus 8 south. So we're going to have 18 meters per second south. Divided by our time interval. Running out of room. And that gives us our acceleration, 360 meters per second, and now our direction is south. Oh, meters per second squared, sorry. South. I'll just pause. Alright, so our last question says, a racehorse takes 2.7 seconds to accelerate from a trot to a gallop. If the horse's initial velocity is 3.61 meters per second east, and it experiences an acceleration of 2.77 meters per second squared east, what is the racehorse's final velocity when it gallops? Okay, so this question is a little different because it's not asking for acceleration. It actually gives us acceleration. So its acceleration is 2.77 meters per second squared east. And if I ever don't use the word acceleration, an easy way to determine that it is acceleration is just the units, because I will always write the units there. So if it has meters per second squared, you know it's acceleration. Okay, initial velocity is 3.61 meters per second east, and it gives us time, which is 2.7 seconds. And we have to find final velocity. So our equation looks like this. Final minus initial all over time. So we need to rearrange this equation. Alright, so let's put in our numbers. You could rearrange first, or you can put in numbers and rearrange. I'll rearrange first. So if we multiply both sides by time, we'll get acceleration times time equals v final minus v initial. And now it's a little bit easier because we don't have a fraction. You can continue to rearrange, but if you want to plug in numbers, that's fine. So acceleration is 2.77 meters per second squared east times time, which is 2.70 seconds, equals v final, which we don't know, minus the initial, which is 3.61 meters per second east. Okay, 2.77 times 2.7. Just grab my calculator. Okay, and I'm going to keep a couple extra digits. I'm not going to do significant digits yet. That should be done at the very end of the question. So I have 7.479, and meters per second squared times seconds actually just gives us meters per second. And we have east. And then let's bring this term to the other side. So it's subtracting here, so we'll add it to both sides. So plus 3.61 meters per second east equals our final velocity. So now we just add those, and we get 11.089, but since everything here is in 3 significant digits, I'm going to round that to say final velocity is 11.1 meters per second east. Right? And then you could put in your therefore statement. Pause that.